right, welcome everybody to this talk on the somewhat esoteric topic of access control in message-driven systems. My name is Marc Klefter. I'm the CTO of a Swedish consultancy firm called Edgement. We focus on cloud-native app development, specifically on message-driven systems. I've been involved with message-driven systems in various scenarios for 20 years now. I'm sure you have as well. How many of you have done any type of pub sub in your life? Several of you. I think, though, the topic of access control has gone largely unaddressed in these systems, with many wondering, is it even a concern at all? So I want to not only explore it in this talk, but also make the case for it. And I'm going to start with introducing the notion of zero trust. Zero trust is an emerging security model which takes, I would say, a hardline approach to how we reason about and treat users, applications in our network environments. And since this is a talk about message-driven systems or architectures, we have to perhaps know a little bit more about what that entails. So we'll look at specifically what types of messages we might encounter and deal with. And then we'll delve into exactly how we'll go about controlling access, enforcing policies, and we'll see how the technology of Open Policy Agent can aid us in that endeavor. And then we'll see the somewhat minute details of implementing zero trust for messaging or the type of communication, synchronous communication, that is our aim, with some recommendations at the end. So let's start by just getting into the right frame of mind. So what we're talking about is access control, also termed authorization. So we're assuming that we have a verified identity of sorts. So we've performed user authentication, and now we're going to use that authenticated or verified identity to access a resource or perform some sort of operation, and come to a decision, is this allowed or denied? You can do that in various ways. There are any number of schemes available, but attribute-based access control is very common, and it's the one that we'll embrace. Attributes, that means that we'll take into account properties of the user, the resource operation that we want to access and execute perhaps, as well as the environment. And for some scheme will enable us to come to an allow or deny decision based on those attributes. Also, the type of system we're studying is a system that is composed of services, or microservices, if you will. I consider services to be more a logical grouping of various processes that communicate with one another. And services can then communicate with other services. But a single service is a logical grouping of processes. You can have, for example, a process where you issue write requests, and another process that you issue read requests to for writing and reading state, for example. And our goal is to take this identity that we have verified and make sure that it propagates to all the services where it's needed, where we need to use that identity to perform access control, which can be tricky. And also the type of communication, as I mentioned, we're looking at is asynchronous. So normally we'll have service-to-service communication occurring directly. So one service directly invokes another. Here, though, we have a broker that decouples services. So they won't have any idea that they actually exist. So the one that produces a message, publishes it, and the one that consumes it are implicitly communicating, but without knowledge of each other. So given this setting of the stage, let's start with zero trust and why that's important or something we're seeing more of. Many of you probably are aware of the old saying, trust but verify, from the 80s, I think. This is a more stringent take on that old adage. So we think more about never trusting anything and always verifying everything. Translated, that means that whatever goes on inside our network boundary in that environment is not to be trusted, or we don't assume anything to be allowed from the get-go. Why is this occurring? Well, the types of applications that we're building nowadays are not that trivial anymore. A distributed application is dynamic, both in terms of how it's composed and how it evolves. It's a number of services potentially that are independently developed and released. They are deployed on-prem, in the cloud, or in a hybrid setting. It's container-based, it's function as a service, there are multiple entry points. It's far removed from the monolithic single process with a single entry point that we might have developed in the past. And also, there's a differentiation between two security levels, if you will. Network security is about firewalls, VPNs, TLS, encryption of data in transit and at rest. It's about routing tables, security groups. That is, of course, a foundation. But on the application level, as application developers, we're more concerned with the identity. Who is trying to enter our system and who wants to perform a certain action or access a resource? Those two layers are unfortunately segregated today, most often. And the representatives of each seldom communicate, and that's typically where trouble starts. And once something enters our network environment, where it's inside the boundary, there are a number of threats to deal with, any types of malicious users or applications that we might have to deal with. Just as an analogy, my Wi-Fi network is secure, I hope, in my apartment. But it's very easy for someone to come as a guest and just ask me for access. And of course, I'll grant it, as a good friend I am. Well, I have no idea what's going on in that person's computer environment, on his laptop, for example. It's not far-fetched to think that we can suffer the same scenario inside our corporate environments as well. So given that zero trust is emerging as becoming critical, let's see how we can enable that in one type of scenario, which is synchronous communication. So I'm not going to go into all the details on this slide. I might assume you have some knowledge about this stuff. For example, of what a JWT is, a JSON Web Token, or access token for short. We assume here that a user has provided credentials and received a token. And every time the user wants to perform some requests, we get a token that is carrying this verified identity. One point directly that I'll state: if the user's credentials are stolen or intercepted in any way, whatever I will talk about won't matter. That's a separate problem about making sure the user handles credentials safely. But assuming that we have a verified identity and credentials are handled correctly, we get it, and we pass it to the API gateway, which performs its decoding of the token, looks at it, and then makes sure that we can continue on with our workflow. So the first thing that happens inside of the gateway, inside our network boundary, is that we do a token exchange, just good practice. So we'll get a separate token, again with the user identity, but it's sometimes limited in scope compared to the original token, and it's only intended for this particular network environment and nowhere else. With this exchange token, we might end up at a first service, so let's say a backend for frontend. So we have a mobile client, we might have a specific service that handles the first incoming requests. This backend for frontend might in turn invoke another service, passing the token along. To ensure several levels of security, we might use MTLS, mutual TLS, between the BFF and the service, so we make sure that those are mutually authenticated. But that's not enough. That's one layer of defense, if you will. The thing we're interested in is verifying the user identity, which is, again, on the application level. So the service that is being invoked will get the token, the ping token, and look at it and say, yes, this particular user might access a document or send an email or something. Now, the nature of this invocation is short-lived. Once it happens, it either completes successfully or the failure. In any case, it's immediate. It stops. And we typically don't have long chains of service invocations. That is significant because if we compare this to the next scenario, which is asynchronous communication, we have something completely different in terms of the longevity of the communication path. So in this slide, we have the same basic scenario. We get an exchange token to our backend for front-end service. But instead of invoking a service directly, we now publish a message to a message broker. And the service consumes it on the other end. Again, on the network layer, we might still use mutual authentication towards the broker, access control lists, all of that good stuff, according to best practices. But there's something else going on the application level. One thing is that we don't really know the address or the host name of the service that is being invoked or implicitly invoked. This is sometimes called location transparency. We're publishing a message to some destination, but we're not aware of its particular naming or other properties we might use to address it. Which means that most often the identity context, the user identity, is lost. It's not part of the message that is being published. Now, location transparency is nice. It gives us a lot of interesting characteristics that I'll go through in a minute. But it does pose a number of problems. Again, we don't know who will consume this. Now, in the future, the workflows, when it happens, could be long-running, could be in a minute, in an hour, or days from now. Sometimes the asynchronous workflow is also requiring manual approval by a human. All of this complicates access controls for us quite significantly. So given all of this in this scenario that we need to consider, let's start to look at some of the message types, the messages that we'll be able to publish to a message broker. First of all, on the left-hand side, we have commands. They are very similar to synchronous requests. Basically, you construct a command, put in some information there, and it's sent to some command handler. We don't know what command handler and typically what happens there, but we express intent. We intend for this command with its information to end up somewhere where it makes sense, but we don't know exactly where. And on the right-hand side, we have corollary, the queries. There are different types of queries, and again, we send a query because we're requesting some results that from a view that we're interested in, but the query handler is located somewhere where we hope our query will be processed. These two are quite similar, but the subscription query might be a little bit different, but by and large, I'll treat them more or less the same. But they're quite distinct from events, and that's probably what you're mostly familiar with. Events are publish, subscribe. They're sent out to one or many event handlers. We don't get any replies. And they are extra, sometimes hard to work with, as we'll see. But there are two large groups, commands and queries, and then events. And we'll take a look at both. So let's imagine a messaging flow. And we'll start with a command. So let's say that we have taken the previous scenario that we showed. We've received a request from an API client. It's been verified. We have the user identity, and the backend for frontend is now sending a command, publishing a command to a message broker. The consumer now will get this command, through what I call a command bus. This is a logical artifact, but you might think of it as being implemented by the message broker. But using this logical construct of a command bus, the command ends up in a command handler for processing of some sort. This could be an order submit command ending up in the command handler that should process it. Now, this will be our first enforcement point. This is where we need to check for access, for proper access. If processing is completed successfully, according to the access control enforcement, we might get an event as a consequence, an order submitted event, say. This event will then be, again, published on the message broker. Here I used, again, the logical construct of an event bus, but it's published through an event bus, which is implemented by a message broker to an event handler. One or several, we don't really know. And in this event handler, we again do some processing, and again we need to check for access control. So we have 2 enforcement points. This is all occurring within one service. But let's say that this service is part of a bigger operation that spans 2 services. So what can follow on? This flow is sometimes called an integration event. We want to notify another service that is part of the overall flow that something happened. And then we have some additional enforcement points in this service. So we call this sometimes an operational workload or a transaction, a business transaction. But as you see, there are quite a few steps involved in this relatively simple workflow, and a number of points where we need to enforce permissions. So given this setup, how do we actually accomplish access control at these various points where we need to check for it? Luckily, we have something called Open Policy Agent, a technology that has gained some popularity in recent years. You can view it as a policy engine for any type of access control schemes that you need to implement. So it's not only for messaging purposes, but anywhere you need to write policies separately, test them, and deploy them. There's some terminology involved, which I won't spend too much time on, but I want to just go through the typical flow when you use Open Policy Agent. And remember, the policies that you create are created separately from your regular application code, sometimes called policy as code. So again, if we have a request coming in to a service, we might somewhere in our code want to, again, enforce permissions. That's called a policy enforcement point, the PEP. It itself doesn't decide on an allow or deny of this particular request. It hands it off to a policy decision point, which actually runs the policy and makes sure to evaluate various attributes. These two are all typically localized together, so they are able to communicate swiftly with another, because we might be evaluating a lot of policies per time unit. And this decision point typically gets a bundle from an administrator point of view, and a policy bundle is your policy as code and some additional data you might always need for your decisions. So a request comes in, you have somewhere in your application code an enforcement point. You then hand it off to the decision point that has a number of data attributes that it can use to evaluate and come to a decision. The decision is then passed back to the enforcement point to your code, and either you can perform some operation, access a resource, or you don't. By and large, this is the overall setup of Open Policy Agent. So if you use this setup for our purposes, for example, for handling a command, it could look something like this. We get a command, the command carries the token with the user identity in a command handler where we want to process this particular command. we hand it off to the decision point, and in this case, if you read the documentation, it would be called the Open Policy Agent server. And the server will decode the token, get the attributes, claims in it, use a number of attributes to come to the decision, and then hopefully we can continue on with processing in our application code. And this would be the same for events and queries as well. But again, if you look at it in practice, where do these PEPs and PDPs end up together? So if you, for example, using Kubernetes and you have a pod with a container for your application code, you would have a sidecar with the PA server or the decision points. So they would be deployed together. So, okay, so we have a way to create policies, deploy them, and we can identify where we have our enforcement points. What are some of the intricacies of establishing a zero trust using these tools and approaches? So let's say that we have an event. We might have processed a command, and now we have an event as a consequence. We want to publish it to any number of event handlers out there. We have, for example, a stock changed event with some payload. The first thing we need to think about is, what is our expiry time? Typically, tokens expire. You have some expiry date that you set when you create a token, or rather, when the authorization server creates the token. Now, this will vary depending on what type of asynchronous flow you want to secure, but typically we'll have to extend it beyond what you normally think of when you think of expiration times. So that would be one thing, especially for events. The other thing that we need to ensure is that the token that we'll be creating and using for an event or any other message is bound to the message. Normally, a token is reused in a synchronous scenario, but here, every event, say, will have a unique token associated with it. We need to create this binding to ensure that the event is not tampered with or intercepted or changed in any way. Which means that the token, if it's leaked, will not really matter because it can't be used for any other purpose but this event, which has an important implication that we'll get to later. And the way we achieve this binding is by hashing the payload, basically. We have a payload that we want to include in this event and publish. We hash it, and it becomes a claim in the token that we'll create. So we see that we have in our token my identity, a long expiration date potentially, and also the hash of the payload. So now we have the event bound to the token. And we also include a specific message ID that will become useful later. So all of this are prerequisites for zero trust. So from our original event, and we generate a specific token, as you can see, and we'll combine that to get our final event that we'll publish, token and the original payload. So given now that we have published an event on a message broker, we have a number of consumers that will potentially get this event and perform some type of operation or allow access to a resource, hopefully. How does event handling look in this case? Well, we'll start by verifying the token. We always do that, using the regular schemes to do when we validate JSON Web Tokens, and what we get are a number of claims or attributes. We can start by seeing if we've had this message received before. Maybe someone intercepted this event and is replaying it for us, so we are consuming it twice. Now, this is why we have a unique message ID, and this is not specific to zero trust or anything. This is usually what you need for at least once delivery, making sure that you're not processing events several times. So we can reject it if that's the case. And then we come to the nitty-gritty details of making sure the event is not tampered with. So we'll take the message hash from our token and compare it to the payload. If they're the same, we have successfully consumed an event that has not been manipulated in any sense. And finally, given these checks, we have our ultimate goal. Check for access, enforce permission. So we'll take whatever resource or operation that is of interest and our claims, my identity, for example, and do the open policy agent check. So the if OPA check is our enforcement point. So this is where the interesting stuff would happen. And it's up to the particular operation, say, what that would be. Again, if this token is somehow leaked or reused, it doesn't really matter because it has no other purpose than being used with this event. Okay, sounds simple enough, but there are always some devil in the details. So one is if you're experiencing a large volume of messages or events, say. Remember, for each event or command or query message that we create and send out, we need to have unique tokens. And these tokens are typically generated by a single authorization server inside of your network boundary. Now, for low to mid volumes of messages, that could be fine. Once you start to scale up, your authorization server could become a bottleneck. One way to solve this is by using something called self-signed tokens. It has some difficulty in practice with certificate chains, etc. So what you will typically see is that you move the authorization from a single point or instance closer, again, to your enforcement point. So in reality, you might see a Kubernetes pod with your application container, your OPA server, as well as the authorization server for maximum throughput. Event sourcing. I don't know if you're familiar with this particular storage pattern, but event sourcing is sometimes used when you want to store all the state transition in your service or overall application as a single source of truth. So you have all your events once they're published, but also natively stored somewhere, potentially forever, because you might need access to them at some later point in time. Now, if you store events, you're not only publishing them and then consuming them, and that's basically it, but you're storing them potentially, again, indefinitely. What happens to your expiration claim? Well, you need to extend it further, maybe a year or several years, or just say that this token will be valid forever, it never expires. Why is that a good compromise? Because again, the tokens do not pose any real problem if they're leaked. That's normally the case why you want to have short expiration times, because if a token is leaked, you want to make sure it expires before it can be used in an inappropriate way. Here, however, again, it's bound to the message, so it's not really a concern if it leaks. But event sourcing is a special case where events and tokens might cause you some headache, but again, you can just set the expiration time to be potentially forever. That's a more straightforward way to solve that problem. And typically, events that you store inside of a service, you can replay them, but you don't replay them when you might have side effects. So for example, if you publish an event, it's consumed, and you send an email notification, for example, when the order has been submitted. If you replay that event sometimes later, there is no particular logic in sending another email notification. So side effects are typically avoided. You're not replaying events across a service, from one service to another. So you can contain this problem a bit in that sense. Finally, sometimes the user identity is not super important. For example, in analytics, if you're just using a real-time window to compute the bolt price for getting from this conference to Malmö Central say, is the user identity that important? If just a general price that we want to present to our Bolt users? Maybe not. We still want to verify or implement zero trust for those events, but maybe I, Mark, my contribution to the price might not be of that big of a concern. So here we can instead use a system role. And it also helps us with something I'll call the user removal issue. So take a look at that. Again, remember that events, once they're created, they are not changed. So they're immutable, and we might store them for quite a while. So what happens if we have a user, me for example, and while I'm the user currently, in 6 months, my account might be removed. But the event that was created now does carry my user identity. So how should we tackle that particular scenario? Well, again, if I'm removed, is this an issue? Well, in analytical scenarios, it could be not that much of a headache, but in event sourcing scenarios, it could be. If I'm not there anymore in the system as a user, should be checked for me anyway once I'm not there. This is where, again, a system role can be useful. So if you see it in the token, instead of my email address, there's now a system user. That role is assigned instead. So we'll use that identity for our events or commands. Could include my identity as well, but if it's not that important in certain workflows, we just have a system-wide user or role that we'll include instead, which will then be used to verify for access control and other purposes. We can also check for this in our policy, permission policy. So in OPA, you have a specific language for creating policies called Rego. And you could, for example, check, is my email present in an array or a set carrying users that have been removed? If I'm present there, and this is evaluated to true during the decision process, we'll just skip access to our resource, say. So user removal is I wouldn't say an edge case, it's common, of course, but it can be solved quite easily. So in summary, why should you implement zero trust? And why should you consider it specifically for message-driven systems? As always, it comes down to what it costs you in terms of time spent, resources required, versus the benefits that you derive. It will differ from organization to organization. But what I like about it is that it puts security aspects at the forefront that you can't avoid. If you have this strict perspective, it means that authentication and authorization can't be escaped or simply put off as something you implement at the end of your application development. You need to take that into account directly from the outset, as you always should when it comes to security, no matter where you're talking about it, but especially here. How would you start? Would you just take a system-wide approach to make this happen? No, you would start with what you could consider critical flows, where sensitive data in your events, say, are present. So basically anything that has to do with money, I guess, would be good candidates. And you can try to start by reducing enforcement points. So say that you have a service, as we saw earlier. Maybe those services can be grouped, or the innards of those services can be composed where you have implicit trust. You will talk to the network administrators. You'll say, I'm going to deploy a service. It might be several processes inside of that service. Can we lock that down very, very hard, so to speak, so that everything that happens in this particular logical grouping in this service is considered trusted? And if that turns out to be the case, well, then you don't have to check specifically according to these schemes inside of that service. Instead, you have fewer enforcement points between services. This is where I, again, encourage application developers to really get down and dirty with the network people, because this is a way to get started more easily. Ultimately, What we want to have happen is for us, application developers, to be able to create new services or update our services, innovate in a sense, while always being sort of in the mindset that our communication paths, whether they're synchronous or, as in this case, asynchronous, will remain secure. And that's a challenge for anyone, but I hope some of these insights today will help you maneuver these challenges in the future. Thank you very much. Maybe we have time for some questions, right? Don't everybody run away and do zero trust all at once. Right. Just catch me afterwards if you have any more thoughts or questions. Okay, thank you.